Welcome to this video on regression. Regression is one of the most important concepts in machine learning. It helps machines understand the relationship between input data and the results we want to predict. Using regression, we can predict continuous values like house prices, stock trends, or temperature, and even categorize outcomes in some cases. In this session, let us explore how machines actually learn these patterns and make predictions using real-world examples. So stay tuned and don't forget to like, share and subscribe to Practical AI Pro for more videos on artificial intelligence. Let us understand what regression means in supervised learning. Regression is one of the most fundamental techniques in machine learning. It helps a model learn to predict an output called the target value based on one or more input features. In simple terms, regression finds the relationship between input variables, which we call x, and output variables, which we call y. The goal is to estimate or predict a value, either continuous like a number or categorical like a class. In everyday language, regression helps machine answer questions such as how much, what value, or what probability. For example, predicting house prices based on square footage and location, estimating sales revenue depending on ad spend, or calculating probability that a customer will make a purchase. This is how regression helps machine make informed, data-driven predictions. Now let us look at two main types of regression techniques used in machine learning. The first one is called linear regression. It is used to predict continuous outcomes. That means numerical values like price, temperature, or salary. For example, predicting the market price of a house or temperature for tomorrow. The second one is logistic regression. Even though the name sounds similar, it is used for categorical outcomes. That means it helps predict clauses like yes or no, spam or not spam, or disease or no disease. In short, linear regression predicts values while logistic regression predicts categories. Both are powerful tools that help machine learn from data and make smart predictions. Let us understand the foundation of linear regression. Linear regression assumes there is a straight line relationship between input and output. It is represented by equation y equals beta naught plus beta 1 into x plus epsilon. Here is what each term means. Y is the target variable, what we want to predict. X is the input feature, the independent variable or the data we use for prediction. Beta naught, also called intercept, is the base value of y when x equals 0. Beta 1 is the coefficient. It tells us how much y changes for every 1 unit change in x. And epsilon represents random error. It captures the noise or unknown factors that model can't explain. In simple terms, linear regression tries to draw the best fitting straight line through the data to make accurate predictions. Here is how linear regression works in real life. In this example, we are predicting house prices based on size. Each point on the graph represents a house, showing its size on the x-axis and price on the y-axis. When we plot these points, we can see a clear upward trend. Large houses generally have higher prices. Linear regression helps us draw a best fit straight line through these points. This line represents the relationship between size and price, showing how the price changes as the house size increases. The goal of the algorithm is to find the line that minimizes the total error that is the difference between actual and predicted prices. This process is known as ordinary least scales or simply OLS. In short, linear regression helps us make predictions like if the house size increases by this much, the price will be increased by that much. Once we build a linear regression model, we need to check how well it performs. Let us look at three key evaluation metrics. First, we have mean absolute error or MAE. It measures the average of absolute difference between actual and predicted values. In simple terms, it shows how far off our predictions are on average. Second, we use mean square error or MSE. Here, we take square of the differences before averaging. This gives more weight to larger errors, helping us identify major prediction mistakes. Third, we use R-square. It tells us how much of the variation in the target variable y can be explained by input variable x. R-square value of 1 means a perfect fit. Now, linear regression makes some key assumptions. The relationship between variables should be linear. Errors should follow a normal distribution. The variance of error should remain constant, and there should be no strong correlation between input features. There are also some variants. Multiple linear regressions uses more than one predicted variable, while polynomial regression adds power of x to handle curved or nonlinear relationships. These metrics and assumptions help us evaluate and trust our regression models in real-world predictions. Let us talk about logistic regression, one of the most popular models used for classification, not regression despite its name. It predicts the probability of an event happening and then assign it to a class using sigmoid function, also called the logistic function. The formula looks like this. P of y equals 1 given x equals 1 divided by 1 plus e to the power of negative beta naught plus beta 1x. In simple terms, the sigmoid function takes any real number and converts into a value between 0 and 1, representing probability. Here is how it works step by step. Step 1, we start with input features like website visits, age, or spending. Step 2, this model applies sigmoid function to convert the result into a probability between 0 and 1. Step 3, then we use a decision boundary, usually set at 0.5. Step 4, finally, we make a classification. If the probability is above 0.5, we predict yes, otherwise no. That is how logistic regression becomes a simple yet powerful tool for classification problems. Now that we understand how logistic regression works, let us see how to evaluate its performance. Unlike like regression, logistic regression uses classification metrics since it predicts categories, not continuous values. Let us look at main evaluation metrics. Accuracy, it tells us the percentage of correct predictions overall. Precision, out of all the predicted positives, how many were actually positive. Recall, also known as sensitivity, out of all actual positives, how many did the model correctly identify. F1 score, It is the harmonic mean of precision and recall, balancing both ROC-AUC curve. This measures the trade-off between true positives and false positives. A higher AUC means a better model. Finally, to prevent overfitting, we use regularization techniques. L1, called Lasso, encourages sparsity by reducing unnecessary weights. L2, called Reach, smooths larger weights so the model generalizes better to unseen data. This is how we evaluate and fine-tune logistic regression to make it both accurate and reliable. Now let us look at some real-world applications of both linear and logistic regression, two of the most widely used algorithms in data science. Starting with linear regression, it is mainly used for prediction of continuous values, sales and revenue forecasting, predicting demand and business growth, energy and temperature forecasting, understanding and forecasting consumption patterns, financial risk modeling used in investment and market analysis, healthcare predictions, estimating patient recovery time or the right dosage levels. On the other side, we have logistic regression, which is used for classification problems where outcomes are yes or no, true or false, or spam or not spam. Spam detection, classifying emails as spam or not. Healthcare diagnosis, predicting whether a disease is present or not. Credit risk analysis, deciding if a loan should be approved. Customer churn, predicting whether a customer will stay or leave. Cybersecurity, detecting login anomalies or suspicious behavior. So, while linear regression predicts numbers, logistic regression predicts categories. Both are powerful tools for solving real-world problems. Let us wrap with key takeaways from linear and logistic regression. Both these algorithms are part of supervised learning, forming the base for many modern AI models. They help deep learning networks learn how to adjust weights and activate neurons effectively. Linear regression is used for predicting continuous values like salary or temperature. Logistic regression predicts categories such as whether an email is spam or not using probabilities. Together, these two algorithms give us powerful ways to solve both prediction and classification problems across industries. Now, let us quickly compare them. Linear regression gives continuous outputs, while logistic gives categorical outputs. For example, linear can predict a salary amount, whereas logistic predicts if an email is spam. Linear output range is from negative infinity to positive infinity, while logistic it is between 0 and 1. Linear models are evaluated using MSC, MAE and R-square, whereas logistic uses accuracy, precision, recall and AUC. And finally, linear regression is truly a regression algorithm, while logistic regression is for classification. So, in short, both are simple yet powerful tools that form the foundation of modern AI learning systems.